Good day to you. Um, Here's an example, the first example in the area of hypothesis test. And so as we make our way from confidence intervals to hypothesis test, we're really just seeing another way to do inference about a population. Or more specifically, we're seeing another way to draw conclusions about a parameter, and we're drawing these conclusions from sample information. More particularly, we're using sample statistics to draw inferences about parameters. One way to do that is through interval estimation. Another way is through hypothesis testing. And again, hypothesis testing deals with saying something about the plausibility of a particular hypothesis being true or not. So can we reject this hypothesis, or can we fail to reject it? That's the sort of thing we're doing here. So here's a first example. On a test on mu, the population mean, when sigma is known, that is, when the population standard deviation is known. Okay, in this example here, using traditional methods, it takes 108 hours to receive a basic flying license. A new license training method using computer-aided instruction has been proposed, and a researcher that used this technique on 140 students observed that they had a mean of 109 hours. And we're going to assume that the standard deviation is known to be 7 hours. Is there evidence at the 0.1 level that the technique performs differently than the traditional method? So is this new method any different than the traditional method? That's basically the question we're asking. And we're going to try to answer that question by looking at the population mean. And so before I get to these the different steps here, I would just want to pull the information out that I have from the above paragraph. Now, X bar, my sample mean, is 109, and that's out of a sample of size 140. So 140 students were looked at, and the average time to get certified or receive their license was 109 hours. And we want to use this 109 hours to say something, and this sample information to say something about the time it takes, or the average time it takes, all students who use this computer-aided instruction to get licensed. Also from the paragraph above, we notice that sigma is 7. That is, it's assumed known that the population standard deviation is 7 hours. And lastly, something else we pick up from here is that alpha is 0.1. That's the significance level. Okay, we're willing to make a type 1 error at a 10% rate. That's what that's saying. Okay, now a type 1 error, again, is falsely rejecting a null hypothesis. In other words, rejecting a null hypothesis when you should not, because it's true. Okay, so what does a null hypothesis look like? What does the alternative hypothesis look like? Well, H naught here, well, let's go to HA first. The alternative, I like to identify the alternative before the null hypothesis, and then once I have that identified, it's straightforward to get the null hypothesis. But in general, the way to think about the alternative hypothesis is it is the claim or the hypothesis that the researcher is wanting to test. Okay, and so the researcher here is saying, is there evidence that this technique differs from the traditional method? In other words, is there evidence to think that the mean mu here is the population mean time it takes to get licensed through this computer-aided instruction technique? Okay, so the population mean time it takes to get licensed through CAI. Mu here, we're saying, is there evidence, we're asking, is there evidence to conclude that this technique is different than the traditional technique, or that the mean time it takes to this new technique is different than the time it takes for the regular technique? So do we have evidence to conclude that mu is different than 108? That would be the alternative. That is the research question here. And so that would mean the null is that mu is 108. Recall that these are complements of each other. Okay, so that's setting up the hypotheses, and this has got to be done correctly or the rest of the problem is wrong. Again, the claim we want to test, we put that in the alternative hypothesis. Okay, so next in hypothesis testing is to compute a test statistic. Once you have your data and you know the hypotheses that you want to test, you compute a test statistic. And this is the evidence from your data. And for us, the test statistic that we use, let me look at the back here of this piece of paper. The test statistics for testing a mean are as follows. X bar minus mu over sigma over root n. X bar minus mu over S over root n. Or T, which is X bar minus mu over S over root n. Now, we use this if sigma is known and our sample size is big, or we know the underlying population is normal. We use this if the sample size is, if sigma is unknown and the sample size is greater than 30 or large. We use this if sigma is unknown and the sample size is small, but we know that the population from which we're sampling is normal. So we have to think about our situation, which one of these would work. Well, we've assumed sigma to be known, and so that would fall under this category, but is n large enough? Well, yeah, so sigma is known, and n is 140 students, and so this is the one we would go with, this first test statistic formula. So, looking at the value of the test statistic, here it's x bar minus mu over sigma over the square root of n. So when I compute this thing, plug in the values, 109, that's x bar. What do I plug in for mu? Well, if you recall, the test statistic evaluates this ratio at the null hypothesis. So at the null hypothesis, what I mean is at the null hypothesis, mu is equal to 108. So I'll plug in 108 for this symbol, or for mu in that formula. And then I divide by sigma over root n. So I've got 7 over the square root of 140. And so you can do that computation, and it turns out you get 1.69. So this is the test statistic from this data in light of what the hypothesis is. And if we think about this, what is it? Well, x bar minus mu is the raw distance that the sample mean is from the mean under the null hypothesis. Okay, so the raw distance is 1. Well, in statistics, we like to measure distance in terms of standard deviations. And so what I do here is I standardize x bar. I take this distance and I divide by sigma over root n, because that's the standard deviation of x bar. And when I divide by sigma over root n, this gives me the number of standard deviations x bar is from 108. So we're saying we are almost 1.7 standard deviations above the null hypothesis. That's what our data is telling us. Okay, the question we'll get to is this far enough away? Is 1.7 standard deviations far enough away from the null hypothesis to reject it? Well, let's go on to answer that question. First, in step 3, we want to specify if the test is one tail or two tail. Well, if we look at the alternative hypothesis, that's where you identify if it's one tail or two tail test, and also, in fact, which tail it's in. This is actually a two tail test because I've got an alternative hypothesis that the parameter is not equal to some value. And so actually, if I want to get even a little bit more specific, if I wanted to draw out the rejection region, that will help me think about step 3 and step 4 in this problem. Here, I've got a z distribution because that's my test statistic, is a z-test statistic. It's a two-tail test, again, because the alternative is that I have not equals to. And what I've got here is I've got to split the alpha in two. So here alpha is 0.1, so alpha over 2 is 0.05. So I'm splitting the alpha, so I've got z sub 0.05 and negative z sub 0.05. I'm splitting the alpha in the two tails of the standard normal distribution. So the area under the curve to the right of z sub 0.05 is 0.05. The area under the curve to the left of negative z sub 0.05 is 0.05. And so my total area here that I've got is 0.05 plus 0.05 or 0.1. That's the significance level. Now, what I'm saying is that if I'm anywhere in these areas, then I'm in the rejection region, right? So the rejection region, or sometimes called the critical region. Well, what is z sub 0.05? Well, we've done this several times, but this turns out to be 1.645 or 1.64, 1.65, either way will work. So this is negative 1.645. So what we're saying is if our test statistic is greater than 1.645 or less than negative 1.645, then we have enough evidence to conclude that this is not true. We have enough evidence to reject the null hypothesis. So when it comes down to the decision rule, we say reject H naught if the absolute value of my test statistic is greater than 1.645. That is, this picture reflects, this decision rule reflects what's going on with this picture. If z is is bigger than 1.645 or less than negative 1.645, then the absolute value is bigger than 1.645. Okay, so I think about that's my decision rule. So in light of the decision rule and the test statistic, what do we do? Well, the test statistic is 1.69. Our test statistic lies over here somewhere in the rejection region or satisfies this decision rule, so we would reject the null hypothesis. In other words, we would reject the idea that the mean time it takes to get licensed through this computer technique is 108 hours. Rather, we have evidence to suggest that it's different than 108 hours. Have we proved that this is true? No, we haven't proved it. That's a strict term mathematically, but we have statistical evidence to say that mu is different than 108.